everyone. In previous lecture, I already discussed recurrence relation of two examples. One is Fibonacci series, another is Tower of Hanoi. So for this recurrence relation, there will be some initial term and the next term we can find by using the previous term. That's called as recurrence relation. Let's see some example. Example 3. Find the recurrence relation and give initial condition for the number of bit string of length n that do not have two consecutive 0. So there should not be 2 0 together. How many such bit string are there of length 5? Now for length 1. Okay, when n equals to 1, there is 0 and 1. In both 0 and 1, there are no two consecutive 0. So for n1, there are two sequence having no two consecutive 0. For n2, there can be 0 1, 1 0, 1 1. 0 0, there are two consecutive sequence. So 0 0 cannot be of this sequence. So for n2, there are 3 bit string, right? Then for n equals to 3. For n3, 0, 1 0, 0, 1 1. There can be two consecutive 1 but no two consecutive 0. 1 0 1, 1 1 0, 1 1 1. So there are 5 bit string having no two consecutive 0. So here for n equals to 3, we can find by adding n equals to 1 and n equals to 2. If we take a1 equals to 2, a2 equals to 3. There are 3 bit string and a3 equals to 5. That we can form by adding 2 plus 3. Okay, 2 plus 3 equals to 5. So we can say an equals to an minus 1 plus an minus 2, right? So here what will be initial condition? Initial condition can be a1 equals to 2 and a2 equals to 3. So these two can be our initial condition. Here in question, it's also asking about initial condition of bit string, right? So we found this is our recurrence relation for n greater than equals to 3. As for a1, it's 2, a2 equals to 3. These two are the initial condition. Now a3 equals to 5, a4 will be 5 plus 3 equals to 8, a5 will be 8 plus 5, it's 13. So how many such bit string are there of length 5 equals to 13? There are 13 such bit string are there for length 5. Next example 4. For this sequence a plus d, a plus 2d, a plus 3d, like what will be recurrence relation? So the recurrence relation can be an equals to an minus 1 plus d. So previous term plus d and n value should be greater than equals to 1. Now for a multiplied r square, ar cube, for this sequence recurrence relation can be an minus 1 multiplied r for n value greater than equals to 1. Just see ar and ar square. So ar square is ar multiplied r, right? Next we will discuss linear homogeneous recurrence relation. So definition of linear homogeneous recurrence relation of degree k with constant coefficient is a recurrence relation of the form a of n equals to c1 a of n minus 1 plus c2 a of n minus 2. It will continue till ck a of n minus k. Here c1, c2, c3, c4, ck are some real number. These are some constant and this ck value is not equals to 0. So if any recurrence relation is in this form, okay, a1 equals to c1 an minus 1, c2 an minus 2 till ck an minus k, then this is linear homogeneous recurrence relation with degree k. Why k? Because last term an minus k. Now the recurrence relation in this definition is linear because the right hand side is the sum of the previous term of the sequence is multiplied by the function of n. And why homogeneous? There are no term occur that are not multiple of AJS. That's why it is homogeneous. Right? With the example, you can identify which one is homogeneous, which one is linear. And the coefficient are all constant rather than depends on n, right? C1, C2, C3, Ck all are constant. And the degree k because last term we expressed as an minus k. So here a0 equals to c0, a1 equals to c1 and ak minus 1 equals to ck minus 1. Now let's see one example. Example 6. The recurrence relation Pn equals to 1.11 Pn minus 1. This is a linear homogeneous recurrence relation of degree 1. Here it is n minus 1, that's why degree is 1, and it is linear as right hand side is the sum of the previous term, okay, and Pn minus 1 we can write as Pn minus 2 format, right, and it is homogeneous as it is similar, right. Now the Fibonacci sequence, this is a linear homogeneous recurrence relation of degree 2. Here n minus 2, that's why degree is 2. Next, a n equals to a n minus 5. This is a linear homogeneous recurrence relation of degree 5. Next, example 7, the recurrence relation a n equals to a n minus 1 plus a n minus 2 square. Here there is a square, that's why this is not linear. All terms are not sum of previous term, right? And the recurrence relation h of n equals to 2hn minus 1 plus 1 is not homogeneous due to this one. This one is not in term of h, right? So for homogeneous, every term should contain a or h, whatever the function name. But here this is a constant. This doesn't contain h. That's why it is non-homogeneous, right? Next, the recurrence relation Bn equals to n. Bn minus 1 doesn't have constant coefficient. Here there is n. N value can be anything. It's not constant. So it doesn't have constant coefficient. Here degree is also 1, right? Let's see some more example. Here all the equations are recurrence relation. From that we need to check which are in order 1, which are order 2 and homogeneous and linear. Now from this recurrence relation, only these recurrence relation are of order 1 and order 2. So here you can see all are n minus 2, n minus 1. So that's why these are order 1 and order 2. Next, which of the recurrence relation are homogeneous? Homogeneous means all terms have at least one of in the sequence, right? Here all these recurrence relation are homogeneous. These two are not, because here there is 3 and here it is multiplied of n. That's why except these two, all recurrence relations are homogeneous. Next we will see which recurrence relations are linear. So here these recurrence relations are linear. An equals to root of an minus 2 is not linear due to this root, and here this is multiplied by n, so it is not linear. Except these two all are linear. Now from this we found that these two recurrence relation are homogeneous, linear and having degree 1 or 2, right? I think you guys are clear how to identify which recurrence relation is linear, homogeneous, which have degree 1 or degree 2 or constant, right? So from this example, only last two, an equals to 3 an minus 1 and an equals to 5 an minus 1 minus 6 an minus 2 are all linear, homogeneous, and this one is degree 1 an minus 1 and here 6 an minus 2, so it is degree 2. In next lecture I will discuss how you can solve linear homogeneous equation. If this lecture is helpful for you, please like, share and subscribe. Thank you.